chemical processing. It has been variously estimated that the capital investment in separation equipment is 40 to 50% of the total for a conventional fluid processing unit. Of the total energy consumption of an average unit, the separation steps accounts for about 70%, and of the separation consumption, the distillation method accounts for about 95%. In general, initial design of a distillation tower involves specifying the separation of a feed of known composition and temperature. Next, I would like to explain on the propylene splitter. Figure 1 shows a typical olefins plant in which a propylene splitter is used for separating propane and propylene. The lighter component, which is propylene, is more valuable than propane. The overhead stream has to be at least 95% propylene. Based on the basic principle for a two-component system, we have to find the minimum reflux ratio and the minimum number of stages to accomplish the separation at rotary flux. For a two-component distillation system, if the relative volatility is constant, then we have the enriching operating line. The last part is debutanizer. Figure 2 shows a flowchart of a fluid catalytic cracking process, and debutanizer is used for separating butanes and lighter from gasoline product. The feedstock of debutanizer comes from a butanizer and is 562 bpsd barrels per service day. Debutanizer is to operate at 150 psid. The design specification will require the overhead product to contain 98.5% of the butanes and lighter components with a contamination of 1.5 more percent pentanes and pentenes. A feedstock component list with molar content. This is a multi-component distillation design and is to fractionate between N-butane and I-pentane. We will use design 2 for both shortcut and rigorous design for the debutanizer.
Assalamualaikum. My name is Nur Syafiqah Lena. I will proceed this slide with the explanation about the process flow diagram. This is the process flow diagram for this petroleum refining process. First and foremost, we'll begin with the enter of the feedstock recycle into the pyrolysis. This is it. And then the product will undergo a compression process, quench process, and then to the demethanizer process. At the demethanizer process, we'll split into two. That is a cold box and the deethanizer. Then at the deethanizer, the product will split into two. That is a ethylene splitter and the depropanizer. Then the product from the depropanizer will split into two distillation column. That is a main of the process in this petroleum refining process. The first is a propylene splitter and the debutanizer. In the propylene splitter, we'll use in the naphtha cracking plant. The function is to separate propane and propylene. In this process, we'll make sure that overhead steam will have at least 95% of the propylene and the rest with the propane. For the debutanizer, we'll undergo this process in the fluid catalytic plant. The function of the debutanizer is to separate the butane and lighter from the gasoline. And then this process will make sure the overhead steam will contain of the 98.5% of the butane and lighter. And the overhead steam will also contain the 1.5% of the pentane and the pentene. The end of the process. Thank you.
My name is Nita. Today I am going to present about the PP splitter for our case study, petroleum refining. For this mass balance, we have feedstock of 50,000 pounds per hour. Is the propylene, which is 70% of pure propylene and contain 30% of propane. We are going to purify the propylene to get at least 95% of propylene. So for this mass balance, we already got the mass distillate, while we are missing off molar flow rate for mass flow rate for distillate and for bottle, while we even have missing value for mole fraction of water. So this is the overall mass balance. This is the first equation. This is the first equation. And this is the propylene balance. And this is the propane balance. To find to find the mole fraction of SDA, we need to calculate minimum reflux ratio and minimum number of stages. Since our case study is based on two-component system, we need to calculate minimum reflux ratio and minimum number of stages to achieve the separation and total reflux. For two component system distillation, we have distillation system, if the relative volatility is constant, the equation will be the equation number 1, and this equation number 2 is the equation given for equilibrium line, and this third equation is for the feed quality where Q is equals to 1. If we combine all these three equations, we can eliminate x and y, and if the feed, since the feed is entered at its boiling point, by combining all these three equations, we can eliminate the x and y. Since the feed enters at its boiling point, the Q will be equals to 1. And we can rearrange the combined equation to find the value of minimum reflux ratio. For this equation, relative volatility is already given, and the XD, XF also given, and we can substitute all the value to calculate the minimum reflux ratio, and we will get the answer 2.4. Next, we have to find the minimum number of stages. The actual number of stages can be calculated by dividing the minimum number of stages with the efficiency of the plate. For the actual number of stages is already given, so we can substitute in this equation and find the value of minimum number of stages. Since the relative volatility is constant, we can use this equation. We already find the minimum number of stages. So this equation is equation number 5, can be rearranged so that we can calculate the value for XB, which is the mole fraction of water for propylene. We can substitute all the value inside and we can get the mole fraction of 0.0163 C3H8, which is propylene. We already got the value for XB. Then we can substitute the value of XB into the equation number 2, which was shown previously. And we will get equation number 4. And we can substitute equation number 4 into equation number 1. And we can calculate the value for the distillate, which is molar flow rate 35377 pound mass per hour. 6. So we can get 1 for 623 molar pound mass per hour. Thank you.
A very good evening. I greet to Madam Asiati and my friends. I myself, Sharan Krishnan. Today I am going to present about process description in our case study. Our title of case study is Propylene-propane splitter in petroleum refinery process. The separation process on petroleum refinery. A crude oil will enter the main system as feedstock and it will obtain a product of propylene gas mixture. Okay. In this separation process, our desired product is propylene with 95% of purity. The gas mixture that produced by petroleum in refining process is propylene with 35 mole percentage. Okay, the content of propylene gas mixture is propylene 35 mole percentage, propane 50 mole percentage, nitrogen 50 mole percentage. Our main objective of this separation is to produce high purity of propylene with 95 mole percentage of purity. The separation process in petroleum refining. It is a very big process because it consumes almost 40 to 50% of the capital investment, and it will also consume around 70% of total energy consumption. Propylene and propane splitter, which will be used to separate propylene and propane. Propylene is a lighter component, but it is very valuable compared to propane. So that is why we are trying to separate the propylene from the propane so that we can gain more profit. Okay. So the whole system is a two-component system. It is a binary mixture system. So throughout the system, we will have to find the reflux, total reflux, minimum reflux, as well as the number of stages of separation. We will use two types of calculation, which is minimum reflux ratio and number of stages. Okay, to find the minimum reflux ratio, we will use this type of equation, which is the relative volatility is 1.11, Xt is given as well as Xf. Xt is 0.95 and Xf is 50,000 lb/mol per hour. Okay, to find the number of stages, we will use this equation. Xd is given, Xd we will need to find. Our Xd is 50,000 lb/mol per hour. From the equation, we will find our minimum reflux, which is 2.4, and the minimum number of stages and then to accomplish the separation at total reflux is 93.65. The mole fraction of water is Xd is 0.0163. Throughout the calculation, we have to find the Xd, the mole fraction of water. It is not given, so we have to calculate by ourselves. So the Xd we can obtain from this equation, which is Xd is given relative volatility of number of stages at minimum total reflux and 1 minus X distillate. The Xd is given. So from this equation, we can find the Xb. So as the overall mass balance, feedstock is given, distillate we have to find, and bottom also we have to find. The mole fraction of bottom Xb, we found out that it is 0.0163. The total molar flow rate of distillate D is 353,771 lb/mol per hour. The distillate we can obtain from this equation as well as this equation, propylene balance. The propylene balance from the system is the thumb rule is input is equal to output. So from that rule, we can find the distillate and bottom. The total molar flow rate of bottom B is 14623 lb/mol per hour. The reflux ratio and theoretical number of stages. Reflux ratio is increased, the number of stages will be decreased. When reflux ratio is increased, the process will speed up so that the number of stages will decrease. When the reflux ratio is increased, the purity of propylene can be obtained even more quicker and faster. So, the reduction of consumption of electrical energy. When the reflux ratio is increased, the process will be even more faster, so that it will separate, the propylene will be separated more quickly, and the process will end and faster compared to a low reflux ratio. It will also decrease the capital cost. The process will be faster and a quick process. Next. The relative volatility. The relative volatility of this process is 1.11, which is given. What is relative volatility? Relative volatility is the difference between the volatility of two components, such as in this process it is propylene and propane. In order to separate a binary mixture using this distillation process, there must be a differences in volatilities of the component. When the volatility of a component is high, the boiling point will be low, so that the process will take a longer time to be separated. So the greater the difference, the easier it is to separate. Next. So, as the conclusion, the optimum reflux ratio is 1.1. The reflux ratio is a sensitive operating variable. The optimal reflux ratio is closely related to feed mole fraction, feed quality, and relative volatility. That's all from me. Thank you.
Good evening to Madam Mazati. Today I am going to present factors affecting the production rate. The first factor is the width of the column. Width of the column. Width of the column, the increased width of the column does not improve the separation of the mixture density during the distillation. The number of trays, which is the height, and the reflux ratio improve the separation, and infinitely the tall tower with minimal reflux or 100% reflux. So one of the factors then, it allows to run a higher flow rate through the tower at the same separation efficiency. Next, the higher reflux ratio for the same throughput, which can then improve the separation efficiency. Whereas the high reflux ratio, it will increase the separation efficiency. The next one is higher residency time, whereas it has more passes and it will bring out a very pure product, which is, it may be 90% pure. The next factor is high capacity trays. High capacity trays can greatly increase the distillation tower capacity. In the high capacity tray, the clearance need to allow vapor to escape from under down corner creates a large down corner opening. It increases the distillation tower capacity, and next is the direction and momentum can also help prevent vapor bypassing up the down corner. Next, it is very cheap and more simple. It also helps to control the frictional loss, and it increases the active area and improve down corner separation without wasting the active area on the tray below to increase the tray capacity. Next. The third factor is multi-down corner trays. Multi-down corner trays are used for for very large liquid loads such as propylene. So it allows a reduction in both the height and diameter of a new column compared to the column filled in conventional multi-pass trays. The vessel shell cost can be significantly reduced, which is the cost of the shell can be reduced with the use of multi-down corner trays. It can provide increased product purities. It will increase the purities, whereas it may be the purity will be about 90% and the recoveries will be increased. It will reduce the reflux ratio or reduce energy consumption or increase the column capacity. The fourth factor is the structure and random packing. Structured packing typically consists of the corrugated metal plates. It creates a large surface area for contact between different places, and next it offers excellent capacity and low pressure drop. It will decrease the pressure and per theoretical stage. It will limit to low pressure application of less than 10 bar of pressure.
My name is Shamita. I would like to proceed on factors that affecting production rate. First factor is high pressure distillation tray and column design. At high operating pressure, the vapor density would increase and therefore lower the required vapor handling capacity. This would lead to the reduction in diameter of column, which would reduce the capital equipment cost. Next is the reflux ratio. Reflux ratio can control the product purity. It also can affect the separation efficiency. The reflux ratio will increase the gradient of the rectified operating line and move its intercept with the y-axis downwards, going in away from the equilibrium line. The decreasing the number of stages required to achieve the separation. Next, feed condition. The state of the feed mixture and feed composition affect the operating lines. Hence, the number of stages required for the separation. If the deviation from design specification are excessive, then the column may no longer be able to handle the separation task. So, some columns are designed to have a multiple feed points, then the feed is expected to contain varying amounts of components. Next factor is ideal stage. Stages are built to maximize contact between the incoming vapor and the incoming liquid. By definition, an ideal stage is one where the vapor and liquid reach the stage in equilibrium state. A key result of the ideal stage assumption is that the liquid stream leaving the ideal stage are assumed to be at their bubble point. That's all.
Hello again. As for the conclusion, to summarize the whole project, I would like to recommend the reflux ratio of 1.10 to obtain a high quality of propylene, which is 95 mole percentage of propylene. There are many factors that will affect the whole process, the whole separation process of propylene and propane, such as for the design, maybe the width of the column and the number of trays. The operational conditional variables that would affect the whole process is reflux ratio, number of trays, and number of stages, as well as the relative volatility. So, from our team, we would like to suggest 1.10 as the optimum reflux ratio to obtain a very high purity of propylene, which is 95 mole percentage. That's all from us. Thanks for watching this video. Please like us on YouTube.